So, guys, good morning. Today, as continuation to 3D viewing that we have seen from yesterday's class, uh, we will be looking at 3D viewing pipeline. So, from yesterday's class, we understood about what is the additional things that we will have to deal with when compared to two-dimension computer graphics. Doing computer graphics in two-dimension, what are the additional things that we will have to deal with in three-dimension, just as an overview. And then we looked at the importance of the camera, or just the viewer per se, and then the viewing plane. Okay, so the view plane is the most important factor in three-dimensional modeling. So whatever you want to see on by the user, or from or the application user, is what is the image formed on the view plane. And we also looked at two different projections. We would discuss these projections with a small pictorial representation that is there further in this slide today. Okay. Three-dimensional viewing pipeline. So like 2D viewing pipeline, we also have a pipeline to process three-dimensional image, right? The first stage of the three-dimensional viewing pipeline is the modeling transformation. So the modeling transformation is basically starts with model coordinates. So the model coordinates is basically, we have modeled a cube, which is basically a unit cube, right? So that unit cube is a unit cube no matter where you place it in the coordinate system, right? So you can have this point as some 4 comma 4 comma 4 to this point as 5 comma 5 comma 5, right? So basically what I mean to say here is the modeling coordinates is the proportional definition, you can say, of the model. So no matter where you place, this is made up of planes which are squares. So the dimension of any square that you take will be 1 cross 1. Or let us say you are modeling a door. Okay, you might model it saying, okay, I have a door where the proportion of this door is 1:2. So whatever the measurement that you take for this door here, that the height of the door will be twice of the width. So this, this is basically the modeling coordinates for you. Now, as part of modeling transformation, what you would do is you would take the modeling coordinates and convert it into world coordinates. Basically, you will keep the model in a three-dimensional coordinate system. That's basically the world coordinate system that you have considered. So what happens to the model? It gets a definition, or coordinate points of that model will actually be defined in terms of the coordinate positions in the world coordinate system. So basically, if you take this cube, right, and place it in the origin, right, then we would get the modeling coordinates what we got for the cube modeling. right? We took it from -1, -1, -1 to 1, 1, 1, right? So we took a modeling of unit cube. We did it in our cube modeling and rotating, spinning the cube program, right? We would get each point will get a coordinate position with respect to the origin of the world coordinate system. So basically, you translated or transformed the model, which was free from, which was defined in its own dimension, or in its own how do I say, with its own properties, probably proportionately, is converted into world coordinates. So it will get a position in the world coordinate system. Once that happens, you will also have a viewer, right? This viewer will have a viewing plane here, right? You will have to transfer. This viewer will have his own coordinate system, right? So he will have his own coordinate system. Now, according to this viewing coordinate system, what is the position of this point? So this, now take this as the origin. From this origin, what is the position of this point? 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 We will have to get that, right? So converting this world coordinate definition into viewing coordinates is basically viewing transformation. So in order to do this, you will have to basically translate this coordinate system into this and rotate it such a way that the x of this is aligned with x of this, the y of this is z of this is aligned with z of this, and the y of this one coordinate system is aligned with y of another coordinate system. So it involves both rotation as well as translation activity. So you would be moving one coordinate system into the another coordinate system. That would give you the mapping of this cube in viewing coordinates, right? So basically, you would get the definition of the object in viewing coordinates. Once that happens, you will have to apply projections. Projections depending on the perspective or the parallel projection. The objects have to be the coordinate positions with respect to the viewing origin. Coordinate positions of the object in the screen or the projection plane, right? The 2D plane. What is the coordinate positions that we get here? This, of course, depends on what types of projection we are doing. If they are parallel projections, then it is quite straightforward. We'll only have to change the z of it. That's all. The x and y will not change. But if it is perspective projection, then the x and y would change, right? So we will have to take care of that, and we'll have to bring this object onto the plane. Once we bring this object onto the plane, we will have to perform normalization. After normalization, we would apply clipping. Of course, this clipping is with respect to the view volume, what we have considered, the front, back, and the left and the right and the top and the bottom. And once we get the normalized coordinates, we would convert this normalized coordinates into device coordinates by mapping the normalized coordinates to the viewport, whatever we have defined. Yesterday we saw the importance of how the viewport would be, right? So we would map it into the viewport, and what we get as a result is actually the screen coordinates or the device coordinates. See, this mapping, we have already seen the normalization to viewport and the window to normalization, normalization to window, right? So we would be looking at these two aspects in 3D pipeline. So this much portion, the clipping we've seen. The clipping, you can extend the Cohen Sutherland with 6 bit outcode. You can apply the clipping for front and back as well there. and this portion we know. So we would only be looking at this viewing transformations and projection transformations and the normalization, right? Any doubts in the 3D viewing pipeline? Any doubts in 3D viewing pipeline, guys? Okay, please answer the attendance, guys. So moving forward, we will look at defining a coordinate system for the viewer, right? So first and foremost thing that we'll have to do in three-dimensional scene visualization is we'll have to select a world coordinates, in world coordinate, right? A position for viewer, right? So basically the position where this is the visualization in world coordinates. So there is here is the world origin, right? So how much is x and how much is y and how much is z for this point origin. This is the viewing point, right? So we will have to define that in terms of world coordinate system. Right. Apart from that, we'll also have to tell a vector called up vector. Why is this up vector used, or what is the relevance of this up vector? Anyone? It is very important for us to know the up vector of the camera or the viewer. Why? Perspective we want to capture. Perspective, okay, what exactly can you... Perspective, okay. So if the up vector changes, the perspective changes. Orientation of world with respect to the viewer, that is correct. So it's like, you know, the orientation, you are up, consider you are the camera, and the top of your head you have the direction with you know, consider a vector which is popping out of your head towards, you know, opposite direction towards the sky. So that gives you your up vector, basically. That's your camera's orientation. That's your eyes orientation. Now, tilt your head towards right side. Did that vector change? Guys, I'm trying to get you a visualization. Please answer this. Okay, how did that vector... so now the vector changed. The up vector changed. Now, up vector changed. Because of that, when you tilt your head towards right side, did the orientation of the world that you see, did it change? From wherever you are sitting now, tilt right side and see, did it change the orientation of the world? Exactly. So now, if you turn upside down, you would see the world in reverse, right? So the orientation of the world changes, right? So that's what the up vector defines. The up vector is to be defined. That is very important. Now, what is a function that we use in OpenGL to specify a camera? Anyone? What is the function that we use in OpenGL to specify a camera position or to keep a camera in the scene or to have a viewer in the scene? You have used it. Yes, GLU lookup. Okay. How many parameters, any idea the GLU lookup takes? Wrong. It's not 6. No, it's not 4. GLU lookup actually takes 9 parameters, where the first position is GLU, the lookup position, the at position, at X, comma, at Y, at Z, basically meaning to say the camera position, okay, and then the viewer position, sorry, not at position, what do I say, CX, CY. I'm just using my own notation. Just hold on, I'm typing something. Yeah, something like this. GLU lookup takes 9 parameters. First 3, CX, CY, CZ here, takes the position of the camera or the viewer in the world with respect to world coordinates. That is in this P0. Right? And then next 3 position will give you the at position. At position meaning to say, it is not always necessary that over here, this camera is looking at the origin. But it is not always necessary that they look at the origin. You might have to look at something else, right? Something else in the world coordinate, some other position. At position is where the camera is looking at. Okay, the position where the camera is directing, or the where are you looking at the camera. Then up X, up Y, and up Z are basically the vectors which will give you the up direction. 0, 1, 0 will tell you the orientation of the camera is basically if you give 0, 1, 0 for up vector, right? In GL you look at, you're actually telling the cameras, consider there is a flag kind of a thing, right? This flag is actually pointing towards, or the vector is pointing towards Y, right? So this is the up direction of the camera. So this is the orientation of the camera, right? If you have 1, 0, 0, then your camera would be looking at the world like this. This will be the up direction. It's like tilting the camera towards the left side, or tilting your head towards the left shoulder, right? Whatever the perspective you would get. Okay, and minus 1 0 0 would actually will be equal to tilting the camera towards the right side, like that. So Z meaning to say you're actually seeing this camera, whatever this camera is there, right? So you are actually seeing this camera like this. Z. Sorry. You are seeing this camera towards Z like this. Right? So that is about the up vector. So we will have to specify view up vector V, which defines the Y view direction. So we will have to, we are basically trying to come up with a coordinate system here for the camera, right? So first thing is we will have to give the up direction. That will give us the Y axis of the camera, right? And we also know the position where the viewer is, and we also know where the position is actually, where excuse me, where the camera is looking at, right? So that is what this says. We also need to assign the direction for one of the remaining two coordinate axes. So we know Y. Now I need to have either X or Z. If I have one of them, I can get the other one by using the cross product, right? So to get the another coordinate system, what we will do is we will specify a second vector, basically, which is along the viewing direction. Meaning to say, where are you looking at? You are going to tell which side are you looking at, right? So that will give you the Z axis where you are looking at for the Z view for the camera, right? Now the projection plane, what you have, that will sit somewhere in Z view, right? So say this is the Z view. Imagine we are looking like this, right? This is the Z view axis. This projection plane will sit somewhere on the Z axis here, along the Z view, right? And the orientation of this also will be with the plane will be with respect to the up vector. The orientation of the projection plane will be same as that of the orientation of the camera, that is with respect to the up vector. I hope you guys understood the definition or what I am trying to say with respect to the camera, the coordinate system, trying to set up the coordinate system, right? I got my Z view, I got my Y view. How do I get my X view? Any guesses? Y axis of the camera is basically, yes, cross product. So Y axis is the up vector, Z axis is the direction with which I am looking at, right? And the X axis I can obtain by taking the cross product between them, right? Now, see here, this image gives you the view plane at position ZVP, right? So this will be your Z view, Y view, and X view. So if Z view is positive, your plane will be somewhere here. If this is negative, your plane will be somewhere here. If it is 0, your plane will be exactly on the place where the camera is, right? Now, this Z view is actually obtained by specifying a P reference point, right? So P reference point is where actually you are looking at this, the direction. Now, can you tell me in GL you look at, are you giving the reference point which exactly in this function parameters, which exactly is the Z, sorry, P reference? Which three parameters are P reference? At XYZ. Yes. So you were telling the camera to look at, right? This second three parameters is the position of the camera where it is looking at. Okay. Now, so we can define a vector, unit vectors along these coordinates. So we can take a normal vector. Oh yeah. See, we will have to know the normal of the view plane is basically the normal which is pointing towards the position where you're looking at, right? So that you can get the normal you can get by taking P reference minus P naught. So you would get the normal vector. So you inverse it, you would get the n, right? You can define a normal vector n, the unit vector like this, and you can also define a unit vector along the up vector, and then you can get the x-axis as the cross product, basically, right, of the up vector as well as the normal what you have. Now see here, this up vector always, whatever user specifies, will not be convenient for rendering the or visualizing, or basically mathematically it might not be convenient. So what your OpenGL or any graphics library would do is they will try to correct the up vector by taking the cross product of these two again, right? So you would get the correction of the up vector. So basically, let us say the user would have given an up vector something like this, and by correction you would get a normal something like this, right? Some difference would be there, relatively negligible. So that would ease up the task carried out by the libraries. So this is visualization of the object, which this is the P reference point. You would have cameras here. You will have a camera here. You will have camera somewhere behind this point, this plane, and you will have a camera here. So they are trying to visualize it, right? This is parallel projection. The viewing planes are like this. You would see this, the side view, this image what is formed, right? They are basically with respect to, they are just projections like what you had done in CAD, right? The top view and the side view, like that. They are just the projections. So it is extremely see, you can try to visualize the scene by redefining. You can basically redefine the scene itself, the object, and then visualize, keep the camera static and try to visualize it. One thing. The second thing is you can change the P reference where you are looking at in by the camera. So the camera position will be static, but you would be moving it from the same position. You're just tilting it in different directions to see the world. That is one second thing. The third thing that you can do is you can change the position of the camera itself, right? And try to see the world in, you can change the position of the camera, but you can keep the look at position constant, and you can visualize the complete object from different aspects. Now, out of all these options, what have we done in our in our perspective cube visualization program? What is constant there and what have we changed? with respect to the camera. Have we kept the object constant and moved the camera, or have we kept the camera constant and moved the object? Are you sure? Ashwin is saying camera is moved, guys. Others, is that correct? Object constant. Yeah, so basically you are keeping the at position constant and you are changing the camera position using a matrix called viewer, right? Viewer of 0, viewer of 1 and viewer of 2. So you are changing the position of the camera, not the this Pref is being constant and you are moving your camera and trying to visualize this object from different angles. That is what you have done. The other thing that you can do is you can place multiple cameras, right, and visualize all of them. You can place 4 cameras in 4 directions and have 4 viewports and try to visualize them, the same object, from different angles. So this demo we will be looking at. Okay, this demo we will be seeing. We'll have a demo where I have placed a tetrahedron and we will keep different cameras in different positions and try to visualize the tetrahedron and try to create viewports and map those objects or the result of those camera visualization into those viewports. Okay, and then we have so this is about viewing transformation. You will have to define a coordinate system first and foremost. Once you have the coordinate system, you can achieve the translation, viewing translation, transformation by translating coordinates, one coordinate system into the other, and then rotating appropriately to align it with X and Y and Z. You would get the definition in terms of viewing coordinate system. That is about view transformation. Now, looking at the next transformation in the 3D pipeline, we have projection transformation. So projection transformation basically are like this, If the viewer is somewhere over here, you have the plane, you project the lines parallelly and you would get this projection on the screen. Now, the major property of the projection, parallel projection, is that the right? You take any parallel lines. If you have parallel lines like this in the object, in the scene, you would see them as parallel lines in your screen or in the plane, right? So in parallel projection, that's why in the first program, Cube program, when we projected, right, we would see the program, all the square as a, square planes, all of them were parallel to each other. That was because it was orthographic projection or parallel projection, right? And second thing is that this point should have been here. You can categorize these parallel projections into 2 types. The first thing is you can project the lines perpendicular to the view plane. So this line is basically the projectors are at 90 degree with respect to the view plane. So it's like cutting directly straight. It's very much straight with respect to the view plane. Object and view plane are aligned and your projectors are 90 degree to the view plane, right? So this kind of viewing or this kind of projection is orthographic projection, ortho, right? The second type of projection is called as oblique projection. Oblique projection is basically where you have an object right? And the projectors are parallel, but the plane is actually, the projectors are parallel to each other, but they are at certain angle which is not 90°, okay, with respect to the viewing plane. They are making some kind of angle which is not 90°. That's the oblique projection. Did you guys get the difference between orthographic projection and the oblique projection? So the projectors are at 90°, oblique it is not at 90°. But in both these cases, the projectors are parallel to each other. So both of them are considered as parallel projections. Did you guys get the idea? Respond, people. Guys, am I audible? See, parallel meaning to say the projectors are parallel to each other, right? The projectors are parallel to each other. So now you have this. See, I'll tell you. Let's say that I have a cube like this. Right? Say my plane is here. These all projector lines are basically parallel to each other and they are making an angle of 90°. Now, instead of that, let us say the projector is somewhere here. So the projection is going like this towards infinity, but they are ultimately parallel to each other. Right? So they are parallel to each other. These projectors are parallel to each other, but they are at certain angle which is not 90°. This is oblique. Did you get it, Ashwin? Yeah. So that's oblique projection. And then we have perspective projection. So this is a good representation of perspective projection. This is the convergence point, or this is the viewer position. All the projectors are actually converging at this point, and the image, the plane, viewing plane is kept somewhere between the viewing convergence point and the object in the world. So whatever the object that is formed on the plane is actually the visualization that you get to see. Now, this projection does not preserve the relative proportion of the object. So if you see, the object size was same in this projection. However, the object has become smaller here. So the farther it goes, the smaller it becomes. The closer it comes, the bigger it appears, right? So that's about perspective projection. So in the next class, we would be looking at matrices for all these. In the next class, we'll be looking at matrices, and we'll also be looking at curves in OpenGL. We looked at circles, we looked at lines. We will be looking at curves in OpenGL. So that's all I have for you guys today. One thing I wanted to ask, out of parallel projection and perspective projection, which is actually realistic in nature? Yes. So perspective projection is actually the realistic projection in nature. So if you are trying to model a game or something which need to be realistic, you would go for perspective projection instead of parallel projection. However, if you are doing some modeling and etc., right? If you are probably modeling kind of a architectural design or something, right? You would go for orthographic projection. I hope you guys got the good difference between the perspective projection and the orthographic projection. Any doubts so far, guys? Okay. So that's all I have for you guys today. You guys can leave. Thank you.